So in this lecture, we're going to talk about hash functions. So this is not specific to Java, more so very in general in computer science. When we're talking about function, right? So you guys know what a function is. It's a black box, right? It takes a set of inputs and it gives you some sort of outputs. Now, in the context of map, right, or hash table, we use this hashing function that we discussed earlier to map a set of key, let's say K, right, to a hashed key value. So this hash key value is key prime. So it's more like a transformation process, right, that you can use to map your key to another one. And then what happens is you can also apply some sort of compression algorithms to, to remap the key to, let's say, key K double prime, right? So this compression algorithms here, and this is a hash. This compression algorithm could be, for example, your modulus, right? When you apply modulus to the size of the your underlying array for the hash table, it constrains, right, all of the value inside the boundary of what you need there. So that's kind of a mechanism that you see a lot in hashing functions and as it relates to hash tables, or generally a map, right, in data structures in computer science. Okay, so we need to also reckon a couple of things. One is when we're using a hash table, lots of time we use what's called the array. We don't use any other data structures. Array is very fast, right? So if you know, let's say if you have an array ARR, if you know the index, right, then the retrieval, let's just say if this is, K double prime, the retrieval of this value, right, ARR at index location K double prime is O of 1, right? And that's what makes your hashing or your hash table data structure extremely fast, because all of the retrieval, what we call lookup, right, is O of 1. So this is lookup or retrieval. That's pretty much it. And if lookup is fast, then insertion is fast too, because you know where it is, exactly where to insert the information from, because what you have here is just an array, right? Nothing else. So there are two factors that impacts the spread of your keys, right? So what does that mean? When you have an array, right, with a number of elements, the slots in there. Now your key is going to be here. It could also be here, right? Or it could also be here. It doesn't matter where it is, as long as it sits inside this array. So the size of the underlying array is important. You don't want to, for example, create an underlying buffer array with several billion elements in it, and that is a waste of memory, to be honest. So people don't do that. And the other thing is, what you need to consider is how many different integer values you have, right? So if you have in computer sciences, let's say if just to solve this problem, you can have no more than 10,000 values, then you can use that informations given to you to basically come up with your own compression functions, compression function C here, or even the hashing function that allows you to kind of minimize the number of collisions, right? So in connections, in conjunction with H and then C, hashing function and compression function, you can devise a specific approach or strategies to ensure that the spread, right, is evenly distributed. If you don't have an evenly distributed spread, then you run into the risk of collision. And collision, as you see, is O of n, right? When you have stuff that gets chained, across the board, that creates inefficiency, because every time you're looking for a key and a remap, that transformation H and C lands you on the same spot. And then you have to go through that entire list, right? From left to right, looking for the specific value that you're looking for. So that is an expensive proposition that you don't want to get into. And that is a hash functions and some of the considerations that you have to have. So when we're talking about hash function, we're talking about the array underneath it. Sometimes you have to also, depends on the problem that you're solving, think in terms of a space, right, versus time trade-off. So what does that mean? One is if the array is large, right? So let's say it's got 2 billion elements in it. So This ensures that you can minimize the number of collisions that way, because chances are, a value is going to be distinct, and assuming you have a good hashing function, these keys will land on, their respective spot. There won't be any collisions. But the problem with that, right, is then you get into the space issues, because memory is not cheap, right, and it is definitely not infinite. So you want to take that into consideration. And the other thing is, when you have, a giant, let's just say, um, first of all, let's say if you don't have a lot of space, in this case, you're going to have a very ingenious device to map, right, your key into a key prime. That's not going to have trade-offs. But then your hashing algorithm is going to have to go through some transformation that takes time. So you may want to do that. You may not, right, want to do that. So sometimes you got to look at, space and time, how long it's going to take, right, and how much space you have, and things like that before you scale your problem up, because you don't want to just solve one problem, right, only this one time. You want to be able to devise a solution that could scale, right, in the future to suit, right, other types of scenarios. So you create reusability, right, in your solution that is a value that you want to create. So hashing system will often monitor their own load. So this is what happens too. Lots of times your array is going to be at maybe 75%, 80%, 90% through. And this triggers what we call a watchdog. And you want to have that mechanism in place. This is a very good stuff to have. So the author uses 75% as an example. So you always want to have that, right? Bear in mind that when your system is on the brink of reaching its capacity, you want to be you want to enlarge, right, the capacity a little bit, sometimes by doubling it. And there are different ways and different mechanisms that you may want to consider, or policies in general, to consider how large, right, the expansion should be when this happens. Sometimes people double, their rate SAS when an expansion happens. So the next time when it reaches 75%, it's again, the entire thing doubles again. This is what we call rehashing. The mechanism involving rehashing. So what is rehashing? Rehashing is also what we call hash table resizing. A hash table resizes, according to the number of buckets you have, right? So typically resize happens when you have to increase the number of buckets, right, while preserving all of the existing items in there. So a typical operation looks like this. Let's say if you have, let me just get rid of this and use red. Let's say initially you have, an array of maybe 4, right? So this is your original size. And due to the 75% trigger watchdog, right, 75%, and it triggers a rehash. Actually, not a rehash. Yes, it triggers a rehash. The first thing it does is it dynamically expands, right, this underlying buffer. So this underlying buffer all of a sudden now, it's got this many, right? So regardless what this is, your new size is going to be n prime, right? So what happens to the elements that you already have in there, right? So recall that, let's just say, just for the sake of illustration, to be on a simple side, these value, right, coming in, they used to be computed, right, using value mod n, right? Yeah, because you want to compress, right, these value into, right, when I say value, they're basically k's. So let's just say this is keys, not values, okay? So these keys are hashed or compressed, right, into this n space in this fashions, right? Now, because of the rehashing, right, because you have to map all of the value inside n into n prime. What this happens is, so when this happens, you basically have to recompute their new locations. So their new locations would be, in this case, k, right, mod n prime, okay? Now this applies to other cases as well, but generally that's what you have to do, right? So new location becomes this. So that's the first distribution, and then for all the forthcoming k coming in, yeah, you're gonna have to mod it to this or compress to the n prime size. So that's what happens as part of the rehashing. And as far as how large, when the expansion happens, how large the size is going to be, this is the policy you can set. Sometimes in the things that I'm seeing where they double the size and then the new size or n prime is greater than or equal to 2 times, right, your original value, which is 2 times n. And this n prime has to be the nearest prime number that's greater than or equal to 2 times n. Actually, when you 2 times n, this is never going to be a prime number. So this is always going to be greater than, okay? So let's just say if n is 11, right? Your n prime is going to be n prime greater than 22. So the nearest prime that is closest to 22 is 23. So your new size is going to be 23, okay? So there's policies like this in the industry that governs how big you can expand. If you look into your code, which is in hashmap.java, this is module as well, you can see the specific enlarged mechanisms out there, and this enlarged mechanism is linear, right? You can see here is current cap plus original cap, so there is no prime number and none of that stuff. Hash table mechanism for enlarging the system to be very, very generic. So that is that. This is what we talked about earlier, where you have a key coming in. You can use the hash function and you get a hash code. So hash code is basically a reformatted representation of that key. So this key could be a string, right? Hash code is going to, lots of time hash code is just an integer. So this is an n. So key does not have to be an integer, right? So keys may not be integral. So it's possible that this key is called data, right? So what happens is your hash function will convert this data into integer. So lots of time, if this is a string, then it's pretty easy. You can just look at the characters. Each character has an ASCII code representation, right? So we know A is, I think, 97, plus D plus T, right? These things, you can add them all up, or you can square them. You can square root them and then add them all up and then compute the absolute value of, right, blah, blah, blah. So there's some mathematical formulations you can do inside this key function. The key to this hash function is so you can pretty much scramble, right, these data into a unique representation of integer, and that's your hash code. And then what do you do with hash code is you compress, right, these numbers into a boundary, supported by your array. And that gives you a hash table locations. So this is an integer as well, right? Because when you compress it, what you need to do, your goal is to get your array index, right? So this allows for random access, right? So if this is an array with an index, and you can quickly find out where it is, and that gets you basically information in O of 1. Now the question is, how long does it take for the entire thing to take place, from key to hash function to hash code to compress function to lots of time this is done with lots of O of 1 multiplied by a factor, and eventually you still get O of 1. But sometimes it may not be. It could be O of maybe n plus 2, right, or something like that. So there's going to be a cost, right, to this hashing place. But we're not going to get into a super details with these things. So lots of time in industry, and the other thing I wanted to say is these functions, there's many types. Sometimes you can have a perfect hash function where it basically maps into the bucket with no collision. Sometimes you can have a modulo, right, hash. So modulo hash basically takes any integer and mod it by the size of the array, as we saw earlier. You can also have mid-square hash, as the name implies. An mid-square hash squares the key, right, whatever this key is, extracts art, right, number of digits. So this R could be 2, could be 3, could be 5, from the results middle, and returns the remainder of the middle digits divided by the hash table n size. So it's easier to describe this, but once you see it in the mathematical formulations, which is beyond the scope of this, you'll see what happens. Sometimes you also see hashing functions that does multiplicative string hash. Multiplicative string hash is what I just said earlier. Let's say if you have this data, what you can do is you can extract the ASCII code value of each character in the string, and then you can do something with it. Sometimes you can multiply this each number. Let's say A is 97, D would be, I think in that case would be 100, right? Or something like that. And you multiply by a hash multiplier, right? Let's say 4 or 4.5 or something like that. And then you can just keep on adding all of that up. So the mechanism, how you like to, utilize your multiplicative, right, string hash is totally up to you. The idea is to create something that's unique, right? Your hash code is unique. Okay, so let's move on because all of this is beyond the scope of pretty much what you see. Sometimes you'll see direct hashing, and that basically just take that key and map it directly into your hash table. But that is if you don't have, your underlying buffer is capable of supporting all of the variations, right, of your key coming in. So this is what we call direct access table. But anyway, creating a hash, there's a couple of things that you have to remember, and that is, like I said before, you have to have selection criteria and your digitizing strategy, as well as your combinations, right? How you combine these things. So selecting specific parts of the key. If the key is coming in as a string, right? Then maybe what you can do is you can select the middle part, square it, and divide it by, right? So that is the selection criteria. And then you can digitize. Digitize means conversion, right? Converting the selected part into an integer. If this is not an integer, then forget it, right? What are you doing with this, this set of data? Digitizing meaning converting into integer, and then you can combine the results. Sometimes you can get creative, taking maybe, let's say if this entire key is a string, you can take the middle part, you can square this thing, and then you can maybe take the polarizing end and divide by two, and then you can add the rest of it up, right, in the middle. So, I mean, this is totally up to you, but at the end, you have to combine the results and make sure that what you get out of it is something that is mathematically unique, right? So there's no guarantee that this is going to produce the same or distinct, hash code, but you try your best. So that's one thing about creating an hash function. So there's other considerations that you may want to look into. So hash code is not unique, right? Do not use hash code as a key. And this is because when you transform a key into a hash code using a hash function, this hash code could be 10,486. And of course, this is not something that you want to have accessing your value at this location inside the array, because your array cannot be that big. So what you need to do is apply some sort of compression, right, to get your hash code within bound that could be supported by your array underneath it. If two entries are considered to be equal, then basically they're hashing to the same value. So this hash value, hash code will be the same. And the other thing that, like I said before, consider the work required to calculate it. So you don't want to have a hash function that takes up 4 or 5 pages. It's at some point this is diminishing value diminishing return, right? The more that you have, the longer it takes to compute it. It suddenly makes no sense for it. So think sometimes simple and see if you can come up with something that is reasonable enough for you to have inside your hash table. So a precise analysis of complexity of the hashing depends on the domain and distribution of the key, right? So there's a lot of those factors. This key generally, if they're all kind of different, not very similar to each other, then chances of you generating a hash code that is unique from each other is great. But let's say if all of the keys starts with, let's say if this key is string, right? Start with S, like SA, SS, right? SC, something like this. Then your range, right, depends on your hashing algorithms. Your range of hash codes would be pretty close to each other, relatively close to each other. Then let's say if your string having a value of AB, right, or DK, right, that is very distinct from each other, as you can see, right? So that is distribution of the key. There's also the size of the table, right? So your modulus, right? So compression, you're modding by the size of the table. If the table is big, then yeah, of course your spread is going to be larger. than a very, very small table, let's say 4, value. In collision resolution policies, there's right. So how you manage collision resolutions to ensure that they do not right collide. But if they do collide, are you going to store them in a linked list, or are you going to create a bucket, or are you going to use what we talked about earlier, quadratic um, probing, or you're using the linear probing, right? So that's that too. So a lot of these things kind of comes into play, but in practice, it's usually not difficult to achieve close to O of 1 efficiency. So hashing is never O of 1, okay? It's going to be some multiplier times O of 1, or maybe there's a small loop out there that calls for maybe 20 iterations. Sometimes it costs money, right? Money is in time and space. So those are the high-level considerations generating a hash.